Can everybody hear me okay? Great. First of all, that was really wonderful talk. I think it's going to be a little bit difficult to follow, but I'll do my best. Yeah, thank you. Today I'm going to talk about some of our work on democratizing protein language models. So over the past 5 to 7 years or so, we've really seen an explosion in the size of large natural language models following the release of the Transformer in 2017 and these initial BERT and GPT models in 2018. There's just been orders of magnitude in growth in the size of these models, which has allowed for real steps forward in the performance of these models, culminating in things like ChatGPT and kind of the latest GPT-4 model. There's estimates that these models have surpassed 1 trillion parameters. Over kind of a similar time period, over a similar sort of time period, we've seen a corresponding growth in the size of protein language models, which are very similar algorithms trained instead of on natural language on protein sequences. The first models emerging around 2018, 2019. And while the largest protein language models haven't quite reached the sizes of the largest natural language models, we're seeing a similar trend in growth. And with just a couple of months ago, ISM3 was released for the first time, 98 billion parameters. So we're very close to crossing the trillion parameter mark. As many of you may know, training these large models is expensive. Not only is there a monetary cost, estimates that the training of GPT-3 costs about $5 million and GPT-4 around $100 million, but there's cost in the energy usage. Struba et al. Estimated in 2019 the cost of training GPT-2 in energy usage compared to human consumptions. And of course, this was in 2019. As model sizes have grown, so too have the corresponding uses of energy needed to train these models. And there's also a time cost. The estimate from Narayanan et al. Is that GPT-3, which is kind of a similar size model as the latest ESM3, was trained on over 1,000 A100 GPUs for a month. So you can imagine that this limits the ability to train these large models for smaller groups, government labs, biotech startups, or academic biology or small computer science groups that don't have access to these large compute resources. Now, of course, as many of you know, the benefit of these large language models is that we don't actually need to all be training them on our own. These models perform what we call unsupervised representation learning, where the kind of internal representations learned by the models are representative of the tokens. So if you look at natural language models, you can see that there are dimensions that correspond to things like gender or country capital, and you can actually transition within this space. And it's been shown that similar properties hold for protein language models. Rives et al. In 2019, the ISMB paper showed kind of a grouping of amino acid representations in the language model by things like charge or polarity. So as a result, as I mentioned, we don't actually need to be training these models completely from scratch. We can train protein language models on this masked language modeling pre-training task, learn these representations, and then apply them as foundation models to a number of different tasks in protein structure, interactions with other proteins, small molecules and metals, as well as other things like protein localization or actually generation of new proteins. And here are just some representative examples. Of course, I'm not covering every way that these protein language models have been used. But this raises the question then, how do we actually adapt these pre-trained models to our task that we're interested in? Kind of a very common approach, especially for these large natural language models, is to fine-tune these language models. So given some small set of data for the task that you're interested in, train a classification head, as well as the actual language model itself. Commonly, you don't actually train the entire language model, but the last number of layers. What has become very common within this field with protein language models is actually using the language model as a feature generator, the so-called protein embeddings approach, where you're not actually backpropagating through the language model, you just train this classification head. And these two approaches have different trade-offs. This MLP approach on the bottom is very compute efficient, but you're potentially leaving some performance on the table by not updating the representations from these language models. On the other hand, the fine-tuning approach, even though you're not training the entire model from scratch, is still expensive in time, in money, and in energy, and is kind of outside the capacity of some smaller groups. So the question we look to address is kind of, what is the trade-off between these two methods? When are you better off using one or the other? And is there a way to... And of course, we're going to talk about parameter-efficient fine-tuning, which is this idea of adding a small number of trainable weights to the language model that allows you to kind of get the best of both worlds. Parameter efficient fine-tuning has kind of I was going to say a long history, long on the time span of the models we're talking about here, right? As the kind of transformer was emerging, there have been methods for parameter efficient fine-tuning from adapters and prefix tuning, and then updates and residual adapters, low rank adapters, and this research continues. Q-LoRa came out very recently. The method we're focusing on today is LoRa, which has kind of cemented itself as one of the more commonly used methods in the past couple of years. LoRa has some really nice properties which make it fitting for language model adaptation. I'll just go over this briefly for anyone who's unfamiliar with the method. The weights of the protein language model are initialized, so you're actually starting with the base protein language model and taking advantage of this representation learning and this transfer learning. Then you have a set of low-rank matrices A and B, which are updated at training time, and these actually constrain the updates of the model. So you're much less likely to overfit, and you're much less resource intensive because you're training many fewer parameters. And one of the nice benefits of LoRa is that because these additional parameters are added in parallel, the weights can actually be merged back into the base weights at inference time, and you have basically zero latency inference. So what we sought to look at in this work was evaluating how parameter efficient fine-tuning and these kind of trade-off of methods can be applied to protein language models and proteomics. We look at two different tasks. The first is predicting protein-protein interactions, and the second is predicting homo-oligomer symmetry. So given a single protein chain, very often it will self-associate and form symmetric complexes. Our goal is to predict which of these symmetries. For protein-protein interaction, we're using a gold standard benchmark data from Burnett et al., which was presented here at ISMB last year. For the symmetry task, we're using kind of an internal database compiled from the PDB, but this data is now released in Kirshigar et al. In 2024. The reason we kind of chose these different tasks is to get an idea of kind of the breadth of this application. This protein interaction task is pairwise. You have two proteins. It's a binary classification task, and the benchmarks we looked at are balanced, whereas the symmetry task, you only have a single chain, but it's highly multi-class. We have 18 different symmetry classes, which are very highly imbalanced. The first thing we find, kind of as a sanity check somewhat, is that this parameter-efficient fine-tuning approach does allow you to train more layers within the protein language model with less GPU memory here. So there's kind of a lot of different lines and colors here, but the most important thing to take away from this plot is the solid line. The parameter efficient approaches consistently use less GPU memory than the fine-tuning approaches for fine-tuning the same number of layers. This allows us to, within the same resource constraints, train more layers of the language model. What we find is that these parameter efficient approaches, both the most parameter efficient, this kind of frozen embeddings MLP approach, and the parameter efficient fine-tuning approach, which require on the orders of hundreds to thousands of times fewer parameters than full fine-tuning, are actually very competitive under constrained resources. If you look at kind of the accuracy, which is somewhat representative for this balanced class of protein-protein interaction, this MLP approach actually outperforms the parameter efficient fine-tuning and the full fine-tuning, and is competitive or outperforms the previous best from the Burnett et al. Benchmark. However, this kind of improvement in performance, or the full fine-tuning still retains an edge for some tasks, right? We don't want to always be using necessarily the parameter efficient fine-tuning or the MLP approach if you have more resources. We find on the symmetry task that full fine-tuning is able to still outperform these other more efficient or parameter efficient approaches. However, using LoRa and parameter efficient fine-tuning allows us to still approach the performance of full fine-tuning. Even though it's not fully as good, it's approaching this performance. And again, it allows you to do this sort of adaptation with significantly fewer resources. Further, as I mentioned earlier, this symmetry prediction task is highly imbalanced. So we can actually dig into the performance to try to understand where the difference in performance is coming from. And what we see is that the improvement for full fine-tuning typically comes for the classes which have less support or have fewer examples in the training data, the somewhat harder examples. this is where you benefit from having an increased number of parameters to train and increased capacity of the model. However, for classes which are well supported, such as C1, C2, and C5, the MLP approach and the parameter efficient fine-tuning approach remain quite competitive with the full fine-tuning. In addition to these two benchmarks, we perform quite comprehensive deep dive into the hyperparameter selection for LoRa to kind of lay a blueprint for how best to apply parameter efficient fine-tuning to proteomic tasks. We study which matrices within the transformer attention to apply these adapters to, finding that the key and value matrices kind of give you the most bang for your buck in terms of number of parameters used. We also look at the rank of adapters. Obviously, having a lower rank to these adapter matrices requires fewer parameters, but with a corresponding drop-off in performance. But what's interesting is that in the original LoRa paper, they show that it's robust to as low as a rank of 1 or 2, whereas we see kind of a cliff in performance with a rank of below 4. And I think what these experiments in total show is that while we can take these techniques from natural language processing and apply them to protein language models, there's still a lot of room for kind of domain-specific innovation and designing methods which perform specifically well with protein language models and the domain of interest, because the takeaways that we find when applying these methods to proteomics aren't necessarily the same as when they're applied to natural language. In addition to the matrices and the rank, we look at the adapting different number of layers and alpha, which is this hyperparameter of LoRa that functions similarly to a learning rate. Finally, we wanted to look at the extent to which fine-tuning and parameter-efficient fine-tuning updated the actual attention values of these matrices. So what I'm showing you here is one protein. This is the PDB code here. This is an NADH dehydrogenase subunit. And what we're comparing is the values of the attention, not the weights, but the actual attention values for the last 5 layers of the language model. These are the ones that we're actually updating for the tuning, both just the base language model without fine-tuning on the top and after fine-tuning on the bottom. And what we saw qualitatively when we kind of looked at several of these was this sort of diffusion of attention, not diffusion in the machine learning diffusion sense, but in the sense of there's more distal attention. The representations of a given amino acid are more affected by the representations of amino acids further away in the chain, rather than this kind of close to the diagonal attention. And we wanted to try to quantify this effect, the effect to which fine-tuning on a specific task caused this diffusion in attention. So you don't have to dig into this entire equation, but essentially we treated the 2 axes of these charts as variables, and we computed kind of a weighted correlation coefficient. So this RXY here quantifies to some extent the diagonalness of the attention, or the extent to which attention is from nearby amino acids or far away amino acids. What we find is across not just these couple representative examples that we show in the paper, but across all of the proteins in our data set, there's consistently diffused attention after fine-tuning. So I think there's still a lot more analysis that we want to do on these attention values, but it was really interesting to see that this fine-tuning with these adapters resulted in more diffused attention and kind of more distal attention for the contacts. We see this especially strongly in the last 2 layers, where it's kind of most important to move from this masked language modeling task of predicting the next amino acid at a single position to learning more global properties of the protein, such as the things that it's likely to interact with. In addition, we find that these attention patterns are very similar with parameter-efficient fine-tuning with full fine-tuning. So this is something that we really wanted to kind of sanity check when trying to understand if parameter-efficient fine-tuning was a viable alternative, not only that we are reaching similar levels of performance, but that actual kind of the interpretable part and the attentions were changing in a corresponding way. So I'd like to thank my collaborators on this work. A good bit of this work was done at, well, an intern at Microsoft Research. So thank you to Meghna, Rahul, and Juan. The symmetry PDB, or the symmetry data from the PDB was largely compiled by Mink Young. And of course, my advisor, Bonnie, on this work. Thanks also to the people from the AI for Good Lab and the Burger Lab that read and commented on this work, as well as the funding agencies. With that, I'll just say thank you. You can read our paper here. We also have a lot of the code up on GitHub, and I'm happy to take any questions at this time.
Thank you very much. Thank you for the great talk. I had just 2 questions. Maybe I missed. So which is the protein language model that you fine-tuned? And the other thing is, have you also explored LoRa, QLoRa and DORA?
Yeah, so for this, we used ISM2. We look at most of these results are from the 650 million parameter version. We also looked a little bit at the 3 billion parameter version, but didn't see kind of a significant increase in the performance of the models. I'd be very interested to see the results with this new generation of ESM that's kind of 100 times larger. And we haven't looked at kind of the latest QLoRa. When this work was started, we kind of focused on LoRa.
Yeah, great work. So with this path approach, there are many possible ways to do it. For example, the choice of a language model, and also choice of a prompt techniques. And then you talk about the rank and the fine tuning. So have you seen any guiding principles or patterns instead of we have to try all of those combinations?
Yeah, I think in terms of the rank, as I mentioned, there's this kind of cliff, right, where you will tend to see slightly increased performance with a higher rank, but that comes in a trade-off to the efficiency. In terms of a recommendation, I would say probably try to go as low as you can before hitting that cliff, because that will allow you to train the deeper layers of the model, which we saw had a larger impact on performance, being able to actually update those representations deeper into the language model. In terms of kind of the other hyperparameters, like I mentioned, we make recommendations on the different weight matrices to adapt. We found that in general, more parameters give better performance, but that the query matrix was kind of not as important. We looked at all combinations. The key and value had the best, but even the key and value matrices alone tended to perform much better than only using the query matrix by itself.